we're going to talk a little bit about bonding and carbon. And of course, this is going to be pretty important to us in organic chem because, you know, organic molecules mostly composed of carbon and carbon-based, and the fact that we have so many organic molecules has a lot to do with the unique ways that carbon bonds. So, just as a little bit of a refresher, obviously, if we were talking about our traditional bonding for, you know, anything, we would draw a Lewis dot structure, and we draw our 4 dots, and, you know, then we draw the stuff that it was bonded to and draw our bonds. But the problem is that this is really kind of an incomplete model of what actually goes on. And the theories behind what actually happens in bonding for molecules, they can vary. We can talk about Lewis dot structures for one thing, and then we can talk about molecular orbitals. We'll mention a little bit about hybridization, and really the fact of the matter is probably somewhere in between all of these models. Because remember, we're talking science, and so we have these models, okay, that are sort of incomplete representations of what the data actually shows us, okay? So while we're going to talk about these models, remember that it's sort of incomplete. So if we had 2 molecules here, or 2 atoms here, and each of them had s orbitals, if you remember anything from your sophomore chem class or your freshman chem class, Chem 1 class, we talked a little bit about how s orbitals are the smallest, or not the smallest necessarily, but are sort of the first orbitals that we talk about, and that they're spherical in nature. So these are atomic orbitals. And what's going to happen is when we bring them together for 2 different atoms, when 2 atoms bond, one of the things that can happen is that the s orbitals are going to overlap. When that happens, it's going to create what we call a molecular orbital. For instance, if we had 2 hydrogens that bonded together and their s orbitals overlapped, now it's going to form one big orbital that's essentially going to go around all of them. What you can see here is that if this was 2 hydrogens bonded together, that there's a nucleus here, and then the greatest probability of finding the electrons is going to be there in the middle. And so we're going to call this a sigma orbital. Sigma orbitals happen in a couple of different ways, but one of the ways they happen is 2 s orbitals overlapping. That gives us a molecular orbital. So what's kind of cool about these molecular orbitals here is that what we do to form those, so let's assume that this was one hydrogen atom, this was another hydrogen atom, is that we had our electron configurations for each individual atom, for the atomic orbitals up here. But when we combine them, we now have in the middle here, we have these molecular orbitals in here in the middle. Okay, and we're not going to go into all the specifics of how this works. I mean, we can talk about some of that in AP chemistry. You can take that next year. Or in your college chem classes. But essentially, the combination of those 2 s orbitals creates a sigma orbital here. And then we would call this a sigma anti-bonding orbital up here. That's not really important to us, though. All that's important to us is that we're going to form molecular orbitals when we overlap our atomic orbitals. Okay, now, so what we might ask if we have things above s orbitals, because even if we're talking about a molecule or an atom as small as carbon, we're going to have p orbitals involved. And if you remember your shapes for p orbitals, they essentially look kind of like this. Remember that we're talking on 3 axes, so we've got x-axis, y-axis, and then z-axis, and of course then we can sort of pull out our orbitals there. So this would be the p orbital on the x-axis, so we would call that p sub x. If we're going to give it a name, so that would be the p sub x orbital. Okay? And so we can also form a sigma bond if we overlap that p sub x orbital on its end with an s orbital. That's going to give us another case here. If we circle this up, this is going to be another sigma bond. Okay? Or sigma orbitals, which form sigma bonds. We can also have a case where we get 2 p orbitals, okay, and they overlap each other end to end, and that then is going to give us another sigma bond there, another sigma orbital right there. Sigmas aren't the only types of bonds that we can have, though. In fact, what often happens, and we'll talk about these later in the year, particularly when we talk about double and triple bonds, is that what if those 2 p orbitals overlap side to side instead of end to end? Well, in that case, we would get what we call pi orbitals, okay, just like the letter you learned in math class. and they look kind of like this little guy here. If we overlap them side to side, we're going to get p orbitals, and that's going to help us in double bonding. Typically speaking, sigma orbitals are often what happens in single bonding. Okay? So, all of that just to lead us into a little bit about why carbon bonds the way it does. So, we're going to take that molecular orbital theory, we're going to combine that with another theory here called carbon hybridization. So, essentially, if we drew the electron configuration for carbon, it looks like this. Okay? So, what matters to us as far as valence is here, what's sort of outlined in the purple here. Remember, valence is highest energy level. Okay, so energy level 2 is the highest level. We've got 4 valence electrons. We kind of know that. We draw Lewis dot structures with that all the time. So what that would sort of lead us to believe, if we look at this then, is it looks like I've got 2 single electrons. And we know that those single electrons like to form single bonds. And that we also know that sometimes if we've got a blank empty spot, that sometimes another atom can donate 2 electrons to form the bond itself, a coordinate covalent bond, we would say. And so what it kind of looks like there is that we should really only be able to form like 2 or 3 bonds out of a carbon. But we obviously know that's not the case just from the structures we've already drawn. Empirically, that's not the case. We know that carbon tends to typically form 4 bonds. And so the way that it's going to do that is we're going to take these valence orbitals here, and we're going to combine these 4 orbitals. We've got 1 2s, and we've got 3 2p's, and we're going to combine them all into one big set called sp3 orbitals. And instead of you having them in 2 different energy levels, remember that's what electron configurations are, 2s is a little lower than 2p. These 4 are all together degenerate orbitals, we would say, meaning they're all in the same energy level. And so if that's the case, if this was our 2 sp3 orbitals, then instead of the 4 electrons being paired here and then 2 singles, we actually have 4 unpaired electrons. And that's good. That's actually what we want because that's what the empirical data shows us. It shows us that what carbon actually does is it tends to form 4 bonds. And this scenario here sets us up to allow that to happen. Now, what sort of might be the question in your head then, or maybe should be the question in your head is, well, we understand what an s orbital looks like. We know what the p orbitals look like because we talked about those in the last couple of slides, and of course in Chem 1. But what do these weird sp3 things look like? Well, they kind of look like this. They're a little bit of a blend. Obviously, we're combining that spherical shape of the s orbital with the sort of dumbbell shape of the p orbital. So we're going to put them together. We get this sort of, I want to say like lopsided dumbbell, sort of. And so this is what one sp3 orbital would look like. But what it actually looks like in carbon is that we've got 4 of those. Okay? And so we've got one sort of through here, and one back there, and there. And what you can see there is that 2 of them, if you can imagine it 3-dimensionally, is that 2 of them are going to be in the same plane. And then this would show that one of them is sort of going back, and then one of them is kind of coming forward toward us. And that would lead to, when carbon formed sort of its simplest bonds, like say a methane molecule, CH4, okay, which we've drawn stuff like that in class. Okay, nice easy molecules. You have to excuse me, I didn't actually put the pen on. I'm writing with the mouse right now. So if we drew that CH4, the shape is going to come out to look something like this. You may remember this from Chem 1. This is a tetrahedral molecule, a tetrahedral molecular geometry, and that's what the shape is going to look like. The hydrogens would be out here at the ends, the carbon would be here in the middle. And obviously that's different than the way we tend to draw them. When we tend to draw them pretty flat. You'll notice here that there's sort of these different little notations on this particular model. So what do those notations mean? So when we want to draw carbon bonding, we're going to draw stuff like that. And we can draw the single lines that we normally draw to show our bonds. But then we've got a couple other things added on. So if you've got a solid wedge, okay, or a little triangle sticking out, that would mean that atom or that bond is coming out toward you, or that orbital is coming towards you away from the paper, or in our case, away from the screen. And if you've got a dashed wedge, that would basically mean that it's going back into the paper or into the screen. So that helps us a little bit to be able to draw and differentiate and get it a little bit more 3-dimensional than the typical flat way we drew it. So if we had our typical methane molecule, this is how we would normally draw that CH4, right? We draw a carbon, we just bond it 4 times to 4 hydrogens, but obviously we want it to look a little bit different than that. So If we drew it this way, that would sort of be representative of this back on the last page. Okay, so let me come back there real quick. So where we've got this hydrogen is essentially coming out towards us, and then this hydrogen then is going back. And actually we could draw it a couple different ways and still have it be pretty accurate. This would show that these two hydrogens are both sort of coming towards me, and that these two hydrogens are going back into the screen. But again, we'll work with some of these 3D models, but essentially that helps us to know how we need to draw some carbon bonds. So hopefully by the end of that, you're a little bit illuminated as to why carbon forms some of the bonds it is. Hopefully it refreshes your memory about some ideas about hybridization, and just a little brief intro into the idea of molecular orbitals that hopefully we'll talk more about in some higher level classes, and maybe even a little bit more later in this year. Thanks, guys.